Hi everyone, I'm Harish. I'm doing my PhD at Virginia Tech, jointly advised by Professor Dillon and Professor Burer. Today, I'm going to discuss novel positioning algorithms that we developed, the analytical framework for evaluating these algorithms, along with the new non-line of sight bias modeling for Monte Carlo simulations. This is the outline of my presentation. I'll start with a brief background and motivation for this work. Then I'll discuss a reformulated iterative parallel projection method we developed for TDOA-based localization, followed by novel two-stage weighted projection method, which not only provides reliable positioning accuracy but also offers low complexity. And then the evaluation framework with a novel non-line of sight bias model for Monte Carlo simulations. Finally, I'll go over the numerical results, followed by concluding remarks and future work. Uh, in general, localization algorithms can be classified based on their performance and accuracy. We have algorithms such as nonlinear least squares and weighted nonlinear least squares, which minimizes mean square error and provide high accuracy. And we also have methods like optimization-based methods and machine learning-based methods, which generally offer high accuracy, but also they are all high complexity. And then the other methods such as parallel projection methods and successive grid search, they offer low complexity but moderate accuracy. Uh, in today's presentation, we'll see one of the algorithms is reformulated parallel projection method to make it work for TDOA-based localization. And we also developed a new algorithm called two-stage weighted projection method, which offers low complexity but also high accuracy. This is particularly useful for edge computing applications such as IoT, emergency applications, and also non-terrestrial networks based positioning, which are typically EV driven. Before getting into key contributions, I'd like to describe typical measurements and terminologies that we use for positioning, especially for this work. Uh, Propagation delay provides information about the distance between a transmitter and a receiver, and then Doppler shift provides information about velocity. And coming to delay-based measurements, the first one is time of arrival measurements. So where the range measurements are collected from number of anchors. When I say anchors, it means nodes with known locations such as UAVs, base stations, and satellites. TOA can be visualized as a circle with range measurements as radius and anchor location as the center. The intersection of these circles provide the location of the target node. It is called triangulation or multilateration in the literature. Similarly, in TDOA, we take the difference between range measurements by taking one anchor as a reference anchor, typically anchor corresponding to the strongest SNR. Here, the circles become hyperbolas, and the intersection of hyperbolas provide the accurate location of the user. In TOA, we need synchronization between anchors and also synchronization between anchors and user nodes. In TDOA, we can relax the synchronization between anchor nodes and user nodes because of the relative measurements. The other terminology is non-line of sight bias. For example, between a transmitter and receiver, we can have a direct path and also a reflected path. A direct path gives us information about distance. A reflected path travels an extra distance because of this reflection, and this is modeled using non-line of sight bias. Especially when the direct path is blocked, we only see reflected path, and reflected path travels extra distance, and that distance or bias is known as non-line of sight bias. We will discuss more about that in the coming slides. And typically, we use dedicated positioning signals for acquiring these measurements. For example, positioning reference signals in 5GNR. Uh, for coming to the first contribution, traditionally parallel projection methods are applicable to only TOA-based localization. So, as the first contribution of this work, we reformulated the iterative parallel projection method in the literature to support TDOA-based localization. So this is how the algorithm works. It's an iterative algorithm. Initially, we have initial location estimate, convergence threshold, and the maximum number of iterations we need this convergence threshold to be met. In this iterative approach, location estimate is iteratively updated using the TDOA measurements and estimate from the previous iteration and using the known anchor nodes. And then we calculate the TDOA residual, and if the difference between TDOA residuals across between consecutive iterations, if it is less than convergence threshold, we keep a counter, and once counter reaches the specified number of iterations, we terminate the loop and uh, collect the final estimate. Uh, the reformulation we came up with was incorporating the notion of TDOA measurements and TDOA residual over the iterations compared to the parallel projection methods in the literature. We'll see a small demo to see how this iterative method works. For example, this block square is unknown node, and blue cross marks are anchor nodes here with known location. This green circle is basically the initial location estimate. Typically, we select nearest anchor and assign it as an initial location estimate, and then we see that the iterative approach, though the initial estimate is far away, it is gradually approaching the true location, and the difference between the final estimate and the true location is because of multipath. Now the key question is, can we include the notion of weights similar to methods like weighted nonlinear least squares for further improving accuracy, especially for challenging conditions such as low SNR? However, calculating these weights are traditionally called normalization factor in weighted NLS, require matrix inversion and matrix multiplication. Therefore, the key challenge here is to introduce the notion of weights with low complexity. So, with that motivation, as part of this work, we developed a novel two-stage framework method with modified normalization. For to explain the novel two-stage approach, we first consider the TDY measurements. As explained in the earlier slide, TDY measurements is by taking the difference between range measurements. Here, assuming B number of anchors, we take the difference between range measurements by taking anchor 1 as the reference anchor. So in the conventional TDOA, because of this reference anchor and the common range estimate in all the TDOA measurements, the TDOA measurements are not independent. So because of which the covariance matrix is non-diagonal, which is what we see here. And to calculate the weights for conventional TDOA-based localization, we need to take the inverse of this non-diagonal covariance matrix, which is highly complex. And similar approach is employed in weighted nonlinear least squares as well. In the proposed approach, we assume the range estimate is available. So I'll explain what is meant by range estimate being available. So by assuming this range estimate available, so these measurements become independent, because of which the covariance matrix become diagonal, and then calculating weights is basically taking the inverse of the individual variance values of these measurements. uh, so this is how the weight calculation is modified in the proposed approach. The second element of the proposed approach is the two-stage approach. Here, when I say two-stage approach, we iteratively refine the location estimate using the accurate range estimate corresponding to reference anchor. So we leverage the fact that the range estimate is presented in all the TDOA measurements and use that information to calculate the accurate range estimate by mitigating the effects of multipath, and then use that accurate range estimate to further refine location estimate. And this happens iteratively. And so does the two-stage approach. This two-stage approach has similarities with turbo decoding principles, where the extrinsic information is exchanged between two decoders to improve error correction. So with that, I'll now move to provide an outline of how the proposed approach works. We first initialize the location estimate and the range estimate corresponding to reference anchor and the convergence threshold and the number of iterations we want this threshold to be met before terminating the loop, and the weights. Then the algorithm enters into iterative loop. First, we update the location estimate using the weights and the TDY measurements and the range estimate corresponding to reference anchor and the previous location estimate from previous iteration. If we compare this location update with the location update we see in methods like nonlinear least squares or weighted nonlinear least squares, we observe that uh, we avoid complex operations like matrix multiplications and matrix inversion by simplifying this weights calculation and location update. So this is the prominent reason for the proposed approach to be low complex. And then we calculate the TDOA residual and compare the difference between TDOA residual with the specified threshold. If it is less than the threshold, we keep a counter. Once the counter reaches the specified number of iterations, we terminate the loop and collect the final estimate. If not, we iteratively update the range estimate corresponding to reference anchor, which will further refine the location estimate. With that, I'll now move to the evaluation framework. So for the evaluation purposes, we start with the generalized signal model with multipath effects and the delay effects accurately captured along with the Gaussian noise. So this is how we look at the TOA error in general in under Gaussian noise. The true TOA estimate TOA is distorted by the Gaussian noise. Whereas in multipath case, the true TOA is distorted by Gaussian noise along with the bias induced by multipath, which is called NLOS bias. So in traditionally, this NLOS bias is modeled using gamma-based distributions, which is disconnected from the underlying propagation conditions and SNR conditions. In order to address that problem or in order to accurately capture the NLOS bias, we developed an analytical framework using Cramér-Rao lower bound. Cramér-Rao lower bound provides a lower bound on the variance of a unbiased estimator. In this case, variance of a TY estimator range estimate. We derived Cramér-Rao lower bound considering the multipath effects and considering this realistic signal model. So we can observe that it is the TY error is proportional to TY error is affected by SNR and multipath and the transmitted signal and of course the bandwidth. And as a special case, we also derived Cramér-Rao lower bound for AWGN as well under Gaussian noise. So we can observe that it is proportional to SNR and the bandwidth, which is captured using the subcarrier spacing and sequence length because we consider OFDM system. And as I said, this gamma is SNR here. Using these two developed models, we define NLOS bias as a square root of variance of the range estimate under multipath minus variance of the range estimate under Gaussian noise. So whatever the difference we see between multipath and Gaussian noise scenario, that we treat it as NLOS bias to essentially. So now we change the TOA error modeling for Monte Carlo simulations using Monte Carlo simulations, especially under multipath, using this particular model. So the true TOA true range is affected by noise W here, whereas noise W is function of NLOS bias, which is the bias induced by multipath, and at the same time variance capturing all the multipath effects and Gaussian noise effects as well. So using this Monte Carlo simulations, we evaluate the proposed algorithms. To illustrate the NLS bias further, we plotted the CDF of TY error in this particular plot. So since this is CDF of TY error, the leftmost plot corresponds to the best performance. So here we are comparing TY error between AWG and multipath, and whatever the difference we observe here corresponds to non-line upside bias. So now we move on to simulation framework. We consider a conservative setup with 6 anchors to avoid overly optimistic assumptions that could artificially improve the results. To conduct Monte Carlo, we sample different points in a specified area uniformly and treat them as user nodes. We consider TDOA measurements for the localization, and for comparison purpose, we consider nonlinear least squares and weighted nonlinear least squares for two reasons. One is there are also iterative methods similar to the proposed methods. The second one is weighted nonlinear least squares is by far the most sophisticated algorithm we have in the literature, which is known for achieving Cramér-Rao lower bound in the case of Gaussian noise. So we compare the proposed methods, especially the two-stage approach with weighted nonlinear squares, and showcase its superiority. And we evaluated different scenarios, including favorable and non-favorable geometry, good and bad SNR conditions. So what do we expect in these evaluations? Just another point. So all the other simulation assumptions, they are compliant with 3GPP. So we consider the realistic assumptions, including the channel model for multipath. So what do we expect in this simulation evaluation? So regardless of the scenario we evaluate, the proposed two-stage approach, it achieves near CLRB performance and either matches or outperforms weighted NLS in all the scenarios, and consistently outperforms nonlinear least squares and iterative parallel projection method. And coming to reformulated IPPM, it offers comparable performance to nonlinear least squares, and also offering lower complexity compared to NLS. We'll discuss complexity aspect after looking at the results. Coming to numerical results, first we consider favorable geometry where anchors are evenly spaced around a specified area. Here we sample different points uniformly and treat them as different user nodes for Monte Carlo simulations. Under these favorable geometry conditions and good SNR conditions, we observe that this is the CDF of position error that we plotted. So since this is CDF, the leftmost plot corresponds to the best performance. So we compare CDF of the proposed methods, comparing with NLS and WNLS and also Cramér-Rao lower bound. So the green curve is Cramér-Rao lower bound. The purple curve is two-stage approach. The red curve is weighted NLS. Black is nonlinear least squares, and the rightmost one is reformulated IPPM. So we observe that though reformulated IPPM provides a moderate accuracy, it offers low complexity. Whereas the two-stage approach, it is as good as weighted NLS in these favorable conditions. And then we evaluated non-favorable geometry where anchors are placed closely with each other, and which decreases the anchor geometry diversity and coverage as well. So in this, we observe that the proposed two-stage approach is superior to weighted NLS, and the reformulated IPPM is comparable to NLS by offering low complexity. And then we also evaluated favorable geometry with low SNR conditions. Even under these scenarios, we observe that the proposed approach, this purple curve is superior to the red curve weighted NLS. And that's at the same time, reformulated IPPM is comparable to nonlinear least squares and also offering low complexity. Uh, I'll end my discussion with computational complexity. So here we compared the computational complexity with big O notation as a function of number of iterations, number of anchors, and number of dimensions. We can observe that both reformulated IPPM and two-stage approach offers low complexity, especially two-stage approach providing superior accuracy compared to weighted NLS. And we also compared the actual number of iterations and the actual number of multiplications, additions as well. Even in this one, we observe low complexity offered by reformulated IPPM and two-stage approach. So now with that I'll conclude my presentation. So basically, we introduced two low complexity positioning algorithms: reformulated IPPM for TDOA and two-stage approach. While reformulated IPPM offers low complexity, it provides only moderate accuracy, whereas two-stage approach, it offers both high accuracy and low complexity, with either matching or being superior to weighted NLS and also providing near CLRB performance. As a continuation of this effort, we plan to extend this analytical framework to examine Gaussian and non-Gaussian regimes. Particularly, we explore non-coherent and hybrid combining methods as opposed to traditional coherent combining methods. This is particularly useful for NTN scenarios. With that, I conclude my presentation. Thank you so much.